All right, so the first thing we need to really think about when it comes to circular motion is just like analyzing what the object is doing that's moving in a circle. Okay, a couple of things that are required for something to move in a circle. You've got to have like a center point, and then here's the mass over here, and if it moves in a circle, then it's going to take this path that looks like a circle, which mine kind of looks like an ovally egg looking thing. So there's probably something, the distance from the center to the path, which, what do we call that thing? The radius. And if it's moving, then this object, this mass right here, will have like a velocity. So far, so good? Okay. Now, the velocity, though, is tangent to the path. So something must be acting on our mass to keep it moving. So maybe this is a mass that's being moved in a circular motion because of a rope or something attached to it. So maybe there's a rope right there. And if you were to draw a force diagram of all the forces acting on your mass at that point, you would have, from looking over the top of it, all I would see is maybe the force of tension in that rope pulling it towards the center, because the rope would be acting on the mass. Now that force is towards the center, but the velocity is this way. So in the next second, if the object is going up, but it's being forced to the left, where's the object going to be in the next second or the next moment? If it's going up, but being forced left, it's going to be like right here. And now its velocity will be pointing this way. And now the force would be still towards the center, because my rope will have moved. So now it's kind of going up into the left, but being forced down into the left. So where's our object going to be later? Like right here? It's going to move a little bit more to, yeah. And so the velocity is going to be tangent, but the force is still directed towards the center because that's where the rope is. Yep.
Does velocity always perpendicular to the force?
The velocity for something moving in a circle must be perpendicular to the force, because as soon as the force is perpendicular to the velocity, we start changing the direction of the velocity so that it moves not in one dimension anymore, but in two. Okay, so then it's moving this way but being forced that way, so we'll have a velocity like right here. Here's our velocity, and here's the force pointing still towards the center. So is there an acceleration? If acceleration is defined as change in velocity over change in time, and velocity is defined as being the magnitude and the direction, is the velocity changing?
Yes.
Because the direction is changing. So if the velocity is changing, there is an acceleration. Even if the magnitude of the velocity is the same all the time, which is weird, and you have to be careful. So the speed can remain the same, the speed can be constant while the direction changes. Therefore, there's still an acceleration. And it's a special kind of acceleration. It's an acceleration that is directed along the path of the force, which is towards the center. So it is a center-seeking acceleration. And so I'm going to put a little C subscript there. So it is the A sub C, which will stand for centripetal acceleration, where the word centripetal means center seeking. I'm not actually a huge fan of the word centripetal because I think that it causes some misconceptions. So if you called it the center seeking acceleration, then I would be just as happy as if you called it or probably happier than calling it the centripetal acceleration. Okay, so to determine this center seeking acceleration, okay, I'm going to look at a zoomed in picture of an object moving in a circle. Okay, so here's the center. And here's my object, and it has a velocity of v. It's at a distance r from the center. And then I'm going to look at it at a second time when its velocity is pointing tangent still to the circle, but it's over here in the second position. It's still r from the center, and it has moved through an equal angle to the vertical. So let's do some geometry here. Would this angle here, I'm going to call phi, okay, be equivalent in magnitude to this angle here that is green that I'm going to also call phi? So this angle is the same as that angle. This is perpendicular. So this is a right angle here, and this is a right angle there. So this angle should be equal to that angle, right? Tangent to the circle here, tangent here, these two angles should be equal. Okay? All right, so if that's true, then let's look at our change in velocity over change in time. Okay? So if acceleration is change in velocity over change in time, and this velocity actually has two components. It has an x component, so the initial velocity in the x direction would be v cosine phi. My final velocity in the x direction would be v cosine phi. Right? We'll go back to the picture there. Okay? And would my initial velocity in the y direction be v sine phi, and my final velocity in the y direction be negative v sine phi? Was there a change in velocity in the x direction? No. So that means there's no acceleration from this point to that point. No, the average acceleration from the initial point to the final point in the x direction is 0. So is there a change in velocity, though, in the y direction? Yeah. So you have final minus initial, which would be what? Negative 2v sine phi. So if phi is equal to theta, I'm going to use a highlighter right here. Let's call this little leg of the triangle that I drew L. That should be equal to this little leg of the triangle L. So let's call those L. L and L. So then what's the sine of theta? L over R. So I'll have negative 2v times L over delta t times R. Okay, now what is the time? So, okay, if you're going to move from this point right here to this point right there, and this is the radius, and you've got theta here, and you've got a theta there that are equal, and this is R. This distance right here would be S, right? Isn't that an arc length? And then S would be equal to R times 2 theta. So, all right, let's make a substitution for time. So if velocity is distance over time, then our change in time will be what? Distance over velocity. And the distance traveled is this arc length, which is the S is equal to R times 2 theta. So we could write that delta t is equal to R times 2 theta over V. So substitute that back in. We'll have a negative 2V sine theta over R times 2 theta over V. So that's what? Negative V squared times sine theta over R theta. Now, if theta is really small, then the sine of theta is approximately equal to theta. And you can check that in radian mode in your calculator. Like if you do the sine of 0.1 radians, what do you get? 0.099. So if the sine of theta is really close to being equal to theta, then the sine of theta over theta would cancel out if theta is really small. So much, much smaller than the picture actually drew. We would get negative V squared over R. Now, why is it negative? We go from moving up in the Y direction to moving down in the Y direction. So if you're going to have something stop moving up and start moving down, like when you throw something into the air, what does it do? It starts by moving up, it stops and comes back down. Which direction is the acceleration? Down. So in the perspective that we're looking at a particle as it goes across this top portion of the circle, we get an acceleration that is directed straight down. Straight down towards the, starts with a C, ends with an enter, the center. So we could say that the magnitude of the center seeking acceleration at any time is V squared over R, where the direction, where it's directed towards the center of the circle. So even if you're on the bottom side of the circle, the same equation works. But the direction would be up because the two signs would be flipped.